2 hours. I can explain so the spirit of loop quantum gravity and how it compares to other approaches to quantum gravity, and give like a summary of the main results, so that maybe on Friday we can talk about loop quantum cosmology, the application to cosmology, and next week we can see 2 other topics. Next week we can discuss black holes and also the dynamics of loop quantum gravity. So today I want to introduce the classical structure, like what is the starting point, what is the classical action, what is the Hamiltonian formulation, and then what is the game of the quantization, what is the idea and the spirit of the quantization. And so as you know, usually we call this approach loop quantum gravity, but some people call it just quantum gravity, because there is this idea which is not specific to loop quantum gravity, which is that it's maybe possible to just quantize general relativity. So some people think that it's not possible to quantize gravity because, for example, in string theory, there is this belief or assumption or result, depending how we see it, that tells us that for example, the interaction, for example, gravity or the other fundamental forces are described by these tiny vibrating strings. And the spirit of this is that we should use these strings as really the description of what is quantum gravity. And this should be really the fundamental microscopic description. But there is this idea that maybe this is not what we should be doing. Maybe we should still try to put together gravity and quantum mechanics. Maybe, in some sense, we can ask the question, why is it a priori impossible to do a simple theory of quantum gravity? In the sense that we know several ways of quantizing systems. For example, if we take a Hamiltonian system, we have several ways of quantizing this system, and it's very debated which way is better than the other one, or which one is more correct. And but obviously, we also have many formulations of gravity. Classically, there are many actions for gravity, many ways to describe gravity. And we have never tried to write down like all the actions for gravity and all the ways to quantize and try to apply everything together. So a priori it's not clear, if we don't do this, it's not clear to say, oh, it's not possible to quantize gravity as it is. And we have to introduce strings, or we have to make other hypotheses about space-time at the small scale, or degrees of freedom, or this is not clear. And so the idea of quantum gravity in general is that we can maybe reconcile really the ideas of general relativity and quantum mechanics, and try to apply like a strict and a clear quantization to gravity. So usually I like to say loop quantum gravity instead of loop quantum gravity, because as you will see, loop quantum gravity comes in different formulations, in fact. And one of them is canonical loop quantum gravity. This is really the canonical quantization as you know it. So following the idea of Dirac and so quantization of constrained system, because we know that gravity classically is a constrained system, like almost all the systems in physics. And the other approach is covariance, so it's the form of a path integral. Covariance, so path integral. Path integral. And this is, people call this spinfold models. So I mean, hopefully at the end of this lecture we'll understand what these spinfold models are and how they are related to canonical quantization. And so this would be the full theory. So if we take full general relativity and apply the quantization techniques to it, but what we can do to make the life simpler is study like simplified models, for example black holes or cosmology. And so within this framework we also have a description of the quantum mechanics of black holes and what happens in quantum cosmology. So we will also be talking about so LQC, so loop quantum cosmology. And so the idea behind quantum gravity is that the lesson of quantum mechanics is that all the interactions around us are described by fields, and these fields are quantized in a certain sense. So for example, they come with quanta or little like microscopic building blocks. And so the idea is that if gravity itself is a field, so the field of geometry, if we import then this idea from quantum mechanics that this field has to be quantized, maybe there is a notion of quantum geometry. So because gravity is a field, but gravity is geometry. So if it's a quantum field, it's maybe quantum geometry. So the idea here is to see whether or not there is the emergence of quantum geometry. And we're going to see that indeed loop quantum gravity provides this description of quantum geometry. And in fact, the whole philosophy and the whole spirit of loop quantum gravity is to try to work with these quantum geometries. And then say that, okay, at the microscopic level, space-time is not continuous anymore, it's discrete. What can we learn from this? What happens if we have these discrete building blocks, these discrete blocks, atoms of space-time? What happens if we combine them together? Can this describe the dynamics of quantum gravity? And so we'll first start with the canonical loop quantum gravity. And the idea, in fact, so loop quantum gravity was born around 1986 with a new idea by Ashtekar that there are like variables that are more like suited for the formulation of gravity. And then once we use these variables, it's much simpler to quantize the theory. And this seems sort of like a natural thing to do because, as I said, there are many, many different formulations of gravity classically. So there are many different actions. For example, we have the well-known Einstein-Hilbert action, so EH. So a four-dimensional manifold, and there is a positive element here, and the Ricci scalar. And so if you write gravity like this, the fundamental field is the metric. It's the metric tensor. But there are many other formulations of gravity with different fields and maybe higher order terms here and many different things. And we think of like what happens if you try to apply the rules of canonical quantization to all these different formulations of gravity. And maybe one of them, with one of these formulations, we can push the quantization further. And so now the story is not only about using like different classical starting points and without thinking about what we do, but the idea is that there is a formulation of gravity which looks like a gauge theory, in fact. And the spirit of loop quantum gravity in the first place, when this was started, was that if you write down gravity as a gauge theory, so something that looks more similar to all the other formulations of the other interactions that we have, which are gauge theories, maybe using the techniques of gauge theory, it will be easier and more suited to do a quantization of gravity. Okay, so the other reason for this is that, so you probably know that, so this is the Lagrangian action, the Lagrangian formulation of gravity in terms of the metric field. But there is also a formulation which is Hamiltonian. So if you want to do a canonical quantization, you have to write down the Hamiltonian for this theory. And so you know that to write down the Hamiltonian for this theory, you have to assume that there is a slicing of space-time. So the space-time manifold M, space-time manifold M is sliced by these paper surfaces here, sigma of t at instance of time t. Yes, so I don't know if you're familiar with this formulation of gravity or so. Stop me and ask questions if there's something that you don't understand or something that you want to know. But so the Hamiltonian formulation of gravity was discovered by people ADM, so Arnold, Deser, and Missner, who took this Lagrangian and put it in the Hamiltonian form. And then once we have the Hamiltonian form, we can use this Hamiltonian to do canonical quantization. And so the form of this Hamiltonian, in fact, or of this action in Hamiltonian form, is the following. So for the Hamiltonian formulation, we have to introduce a time parameter, because the Hamiltonian formulation requires a time parameter. So this is given by this foliation, so constant time hypersurfaces and a time direction. And then what we get is essentially QAB, EAB. I will explain all these terms. Minus MH HA. And so this is what we call the canonical term. So these are the canonical variables. So this means that this canonical variable is the spatial metric. So this QAB is the metric on the spatial slice. So we have metric QAB. And PAB is its conjugate momentum. So what we have is a phase space, in fact. So we have a symplectic manifold. It's a phase space with the coordinates QAB and PAB. And on this big phase space, there are constraints acting on this phase space. And these constraints, in fact, they are just the translation at the Hamiltonian level of the diffeomorphism invariance. So this action is invariant under 4-dimensional diffeomorphisms. So it's natural, expected, so this shows that there's no mistake in writing the theory like this, that at the Hamiltonian level we recover the generator of this diffeomorphism. And what these constraints mean, in fact, these constraints, so HA, so there are 3 such constraints, because A is running from 1 to 3. So this is a spatial constraint, so this generates spatial diffeomorphisms, and this H constraints generates time reparameterizations. So these encode the symmetry, the Hamiltonian symmetries of the theory. And so what people tried to do in the early years of quantum gravity was to quantize this Hamiltonian formulation, in fact. And so if we take, so I didn't write it down here because it's not going to be useful for us, but if you write the Hamiltonian, so this is called the scalar constraint and this vector constraint, so these 2 constraints of Hamiltonian gravity, we can try to quantize them, so to promote these fields, the metric, spatial metric fields to operators, and then try to give a meaning to these operator constraints, and try to do quantization like that. But this was shown to be very problematic in the early years of quantum gravity. So this is the most naive thing to do, in fact. So because we know that we can quantize any theory for which we have an action, we can put it in the Hamiltonian form, then look at the structure of the constraints at the Hamiltonian level, so follow Dirac's procedure, and then try to quantize this constraint system. So there is a well-defined procedure for this. But the problem is that if you try to apply this to gravity, which is a priori natural thing to do, we run into very big mathematical problems. Because these constraints are very complicated, they're not polynomial or even analytic functions of these space-based variables. So these are very complicated constraints. So if you want to regularize them, to introduce like a well-defined self-adjoint Hamiltonian operator like we want to do in quantum theory, it's notoriously like very problematic with this formulation. And nobody knows so far how to do this. So if we use this formulation, there is no known way to quantize this theory. There is no known way to give a well-defined meaning to these quantum operators. So the idea is that there is, of course, other formulations of gravity, and one of the other formulations is the so-called first-order formulation. So this is the so-called second-order formulation of gravity, because here you have second-order derivatives of the primary field, so of the metric field. And the reason for this is that in this formulation, so in the Einstein-Hilbert action, so the curvature R is a function of the Levi-Civita connection, but the Levi-Civita connection is a function of the metric, in fact. So this object has derivatives of the Levi-Civita connection, the crystal connection, but the connection itself has derivatives of G. So for this we have second-order derivatives of the metric. But what we can do is consider, in fact, the metric and the connection as independent variables. This is allowed, in fact, by the Einstein-Hilbert action. So, for example, instead of performing variations of this action with respect to the metric to get the Einstein equations, what we can do is do variations with respect to the connection and the metric independently. And so there is a way. So, are you familiar with the first order? Is it okay? And so, in fact, there is a more powerful way to write what we call first-order gravity, and this is by using the spin connection and the tetrads. And this was introduced primarily to couple gravity to fermions, because if we couple gravity to fermions, we have to write gravity not with this Einstein-Hilbert action, but with the first-order action. Because the fermions, they know about the representations of the Lorentz group, so the internal group. So what we can do is introduce some new fields. This field EI mu. So mu here is a space-time. This is a space-time index. So running from 0 to 3. Yes. And I, in fact, is an internal index. So I is an index in Minkowski space. So this, if you want, is an isomorphism between so locally between the space-time, so where the index mu lives, and a local inertial frame, so Minkowski space. This is internal space. And so there is in fact a very simple relation between these fields. So these are one forms. This is a collection of one forms, this field and the metric. Because in fact the metric G mu nu is simply given by this, the contraction of E nu, E j nu, with the Minkowski metric. So you see that now if I perform Lorentz transformations on the index I and j in these tetrads, this is invariant. So this is Lorentz invariant in this sense, because there is this Minkowski metric here. And so if you want to write gravity in terms of this field, you also need a connection. So the connection is also one form. It has one space-time index, so it has two internal indices. And in fact, it's anti-symmetric in these indices. So this is equal to minus JA. And the reason for this is that this object carries a fundamental representation of the Lorentz group. So this is valued, if you want, in the Lie algebra of the Lorentz group. So this is a one form. So valued in SO31. So this means that there is a connection. So the analog of the Levi-Civita connection in this formulation is simply this object. So it's omega, but omega is omega mu ij dx mu t ij. So this is the basis of the one forms, and this is a generator of the Lie algebra of the Lorentz group. And so if you write gravity in terms of these variables, in terms of this tetrad and this connection, so the action becomes what we call the Hilbert-Palatini action. So you see already that this is closer now to gauge theory, because we have this internal gauge group here. So there is now a sort of duality, a doubling of the symmetries of the theory, because we have a space-time index. So before the metric field, this metric field knows only about the space-time indices, but these fields now they are a bit extended. They know also about the internal space. And so if you write gravity in terms of this, of these variables, this is HV, so the Hilbert-Palatini action, and this action is a functional now of E and omega independently of these two variables. So we have four manifold. And here we have this. And so this wedge product here is the wedge product of forms. The definition of this is simply that there's another. So an epsilon, so this is the completely anti-symmetric epsilon tensor. So this one is now in space-time indices. This is in internal indices. A, E, I, U, E, J, U, rho, sigma, omega, and B4x. This is in fact strictly equivalent to the Einstein-Hilbert action. So it's just another way to write the action for gravity. It's completely equivalent. So this F, in fact, so F here is the curvature of this connection. So F so where? The omega. So just like in gauge theory, in Yang-Mills theory, for example, so this F is the curvature of the connection omega. So this object, in fact, is the analog in this formulation of this curvature, in fact, of the Riemann tensor. If you want the Riemann tensor, but written in different basis with a different set of indices. But the key idea here, the key concept is that if you write gravity in this formulation, so now E and omega are independent variables, right? So it's a big difference with usual gravity, because in usual gravity, there is only one dynamical variable. There's only the metric. So if we take the Einstein-Hilbert action, we just have to do variation with respect to the metric to get the Einstein equations. So here, if you do the equations of motion, we have to vary with respect to omega and with respect to E, in fact. And so what happens is that if you look at the equations of motion now, let me just look at. Now we have to do. So there are two sets of equation of motion. So the one with respect to delta S with respect to delta omega equals 0. And so this tells us in fact that. So here this is a covariant derivative of omega in fact, with respect to the connection omega. So if I do the equation of motion with respect to omega, I can do an integration by part here. So put this covariant derivative on these tetrad fields. And so what I get in fact is simply, so here I put the indices aj mu, what we get is mu sigma and so the meaning of this equation, this is a well-known equation in gravity. In fact, this equation is telling us that the connection has no torsion. So this is the so-called torsion-free condition. I think people also call it the Cartan structure equation. And so this is in fact, this equation is responsible for the fact that, in fact, we can write here a priori the connection and the E field are independent variables. They're completely independent. So we vary independently the action with respect to the connection or the tetrad. But what this equation is telling us, in fact, this equation of motion is telling us that you can rewrite completely the connection in terms of the E field. This is completely analogous in the Einstein action to writing the Levi-Civita connection in terms of the metric G. Because in fact, so this equation can be solved. So I can write this. So this equation can be solved to get in fact omega mu as a function of E. So there is an expression for this which is not interesting, but the expression for this connection is exactly the same one as this connection, but it's just written in another basis if you want. Instead of being written just in space-time indices, it's written with respect to this new map, so this isomorphism going to internal space. This is why there are more indices here, but the structure, the physical content of this formulation is exactly the same one as in the Einstein-Hilbert action. It's the exact the same physical structure, just the variables are a bit different.
But there are differences in GR, right? Because the Palatini formalism can give us different results from the metric approach.
Yeah, so in fact, so here, so we could do the same thing with Einstein gravity. We could vary the action. We could do two things. We could vary with respect to delta S, delta gamma, and delta S, delta G. So generally we never do this because in general gamma is a function of G. So there is no reason to do this. So if we do this in fact, and if we don't assume anything about the connection, because you know that the connection, so given any connection, it can has what we call non-metricity. So usually this connection, gamma, is assumed to satisfy d mu in rho equals 0. So this means that this connection is metric compatible. And the other condition satisfied by this is that gamma mu, so it is symmetric in the bottom two indices. So this means that the connection is compatible. This means that the connection has no torsion. And so in fact, if we do these variations separately and assume only one half of this condition, so just assume this, that the connection has no torsion, automatically we recover this equation. So if you assume that there are no sources of torsion, and usually if there are no fermions, there is no torsion. So if you have no fermions, you have no torsion. But then if you do these two equations of motion, if there is no torsion, automatically you will get this condition. So automatically you will end up again with the Einstein-Hilbert action. So here sort of the same thing is happening. Here the same thing is happening because we think that E and omega are different independent variables, but if there is no torsion, so if this is equal to 0, So if there are fermions, this will not be 0. With fermions, there will be additional terms here. But if there are no fermions, so no sources of torsion, this is 0, then we can invert this equation, write the connection in terms of E, and then this is in fact the Levi-Civita connection. It's the Levi-Civita connection, but written in terms of G, it's written in terms of E. But it's the exact same physical thing. Is that okay? Yeah, so the other equation of motion, the one we obtained by varying with respect to E, this is only 1/2, this is only with omega. Now we can do with respect to E. So delta S, delta E, 0, this gives us Einstein equations. But only if the torsion is vanishing in fact. So if we first do this variation without using this, then apparently this is not the Einstein equation, this is some other field equation. But then if we use the fact that omega is not any omega, it's not any one form, or it's omega as a function of E, then this reduces to the Einstein equations. So this is just to tell you that there is this classical formulation of gravity which is exactly equivalent to the Einstein-Hilbert action. So depending on what we do, if we use fermions or no fermions or what we want to study, it is sometimes more convenient to use this or to use the Einstein-Hilbert formulation. So for example, people doing numerical relativity, so numerical gravity, they want to use the Einstein-Hilbert action because it's way simpler to work with. This is a bit more complicated because it has all these indices and more structured, but physically it's the exact same thing. So then there's an important difference if you want to quantize these theories. If you want to do quantum theory now, there will be a very important difference. So in fact, you can notice that it's possible to add many terms to this action. This is not the only Lagrangian that gives you a well-defined action principle and the good equations of motion. You can add, for example, a cosmological constant and what we call topological terms. So topological terms are also functions of the curvature, but they will not contribute to the equations of motion. They will just be here in the Lagrangian, but they don't contribute at all to the physics, to the equations of motion. And one such term, in fact, it's possible to add such a term to this action to define, so let me introduce this new action now, which I call the Hawks action. And 4, so it says again, but now what we can do is add, let me put a coupling constant here, so a free parameter that I call gamma, and now I write the same thing but without this epsilon tensor. So without this tensor. So now I just write EI J F AJ. And so the reason for which this exists is that in fact on the Lie algebra of the Lorentz group, so SO31, so once again this is valued, these indices, they live in an internal space. So not in space-time, but in an internal Lorentzian space, so in Minkowski space. So you can choose if your theory is Lorentzian, so I is an index in SO31. If it's Euclidean, it's in SO4. So you can choose depending on what you want to describe, what your signature is. And so in fact, if I take now two objects, for example, T ij and P ij valued in the Lorentz algebra, so in SO31, and I take the trace of these two, there are two ways of taking the trace in fact. So there are two traces on the Lie algebra SO31. One of the traces, so trace 1 of T, P, is just T ij, P ij. But the other trace, trace 2, is the same thing but with the epsilon now. You can use this tensor. So in 4D, so on the Lorentz group, or an SO4, this tensor exists. There is this object, so I can use this object to do a different contraction of the indices. I can do epsilon aj KL, Taj, TKL. I can use this trace in fact. And because there is this freedom in some sense, we can add this other term here. This is just a side, just a remark, but what is very important is that now we can ask, okay, but is this still a formulation of gravity in fact? Because now I take, this is gravity and I add this term. So what does this describe? Is it still gravity or is it a different theory? And in fact one can show that that if the torsion is vanishing, let me remove this. So this term, in fact, this this is zero, in fact, because of the Bianchi identity when torsion is vanishing. So maybe I have the expression of this in terms of yeah, so this is written in terms of f, but this thing, in fact, can be written as a sigma r. Okay, but this is zero. So if I just use this, if I use this curvature, if I write it in terms of the original, in terms of the Riemann tensor, I get just this thing, but this is the Bianchi identity, so this is zero. This means that this term we can add it to the Lagrangian, and it will never contribute to the theory because it's because of the Bianchi identity. So when torsion is vanishing, so when this is a function of E, this term is just zero. This means that this term does not contribute, in fact, to the equations of motion. So we can add this term. It will not change the equations of motion. It's not going to change anything to the physics of the theory. And there are in fact other known terms like this one, other topological terms that you can add and maybe study their influence. But in fact what we will see is that this parameter is very important in loop quantum gravity because it's the existence of this parameter, of this term, that will enable us to have the well-defined Hamiltonian formulation. So now we have this action, and we can ask, okay, what is now the way to try to quantize this theory? So first, I haven't told you why I want to quantize the theory with this action, or why we try to use this starting point, in fact. But you will see in a minute that there is a deep reason for which we choose this action, and for which if we start with a slightly different action, which has the same equation of motion, we are immediately stuck. We immediately have problems and we cannot do the quantization. And so the idea is now to go to the Hamiltonian. Hamiltonian formulation. And so as you know, the Hamiltonian just consists in using this splitting of the space-time manifold and into these Cauchy slices, sigma of t. But so, to do this here, it's very simple in some sense, because here, let me just take this term and write it so the Lagrangian is sigma e. Let me just focus on the first term, just to illustrate what happens. So just the first term. If you want to look at the Hamiltonian formulation now, it's simple because we just have to separate these indices between space and time. So these indices, so mu is 0, 1, 2, 3. So 0 is the time-like index, and 1, 2, 3 are the spatial indices. And so for aj, kl, it's the same thing, in fact. A, 0, 1, 2, 3. So What we can do is now write all the contractions of these indices, like expand the sums and single out the 0 components and the 1 to 3 components. So this I will call in fact 0 A, and this I will call 0 little I. So for example, this object here, this Lagrangian, is equal to 1/2. So I can place the 0 here, for example, 0 A J cal sigma, and then the 0 is E0 I sigma, plus all the other terms of this. And now we also have to split the internal indices, so these indices. And so, okay. So the idea is that there is one simplification that we can use. So simplification. So in fact, I can write this matrix. So this tetrad is a 4x4 matrix in fact. So there are 4 internal indices and 4 spacetime indices. So we can just write this matrix here. So this has 0, 0 components. So these are the E0 A, I 0. So this is a 3x3 matrix here. This is a 3x3 matrix. This is just 3 components here and 3 components here. And this is E0, 0. And in fact, what we can do is use a gauge. We can do a gauge fixing of this action. In fact, we can use a gauge in which these components are 0, in fact. And we will see why these components are 0. I 0, and this is 0. Because you know that in the Hamiltonian formulation of the Einstein-Hilbert action, some components of the metric become the lapse and the shift. So these two are Lagrange multipliers that we had in the Hamiltonian. So that multiply the scalar and the vector constraint. And so here in fact the same thing happens because these, so E0, 0 is the lapse in fact, is what we call n, lapse. This is 0. And this EI0 we can write it as NA, EIA. And NA is the shift. So these are the usual lapse and shift of the ADM formulation, but written in terms of these variables. And the spatial metric, so GAB, is just EIA, EJB, and theta AJ. So this means that if I know EIA, so this is the triad now, let's call this the triad. So if I know the triad and the lapse and the shift, I know completely the metric in fact. So this means that I can always choose this gauge. This doesn't have any influence on the physics or what I described. It's just a big simplification for the action. If I choose this gauge, I have the triad, which in fact encodes the metric. It's the same data, the same contents, and I have the lapse and the shift. So if we do this now, it was noticed that in the 90s or the late 80s, so by Ashtekar, Barbero, and Imirzi, that now we do the analysis of this action, so of the Holst action, so with this additional term, and use this gauge, we can do 2 changes of variables, very clever change of variables. And the first one is to introduce so A, I, A. And the other one is to introduce EAI, which is 1/2 of epsilon ABC. And why we do this? Because these are in fact 2 natural variables that appear if we decompose this action in fact. Because when we split the indices, you see that here we have, for example, epsilon AJK and an epsilon in internal in space-time, and then the product of 2E. So So this object, we can just call it capital E, for example. And also you will have combinations because the curvature here, this is a functional of omega. This is a functional of omega. Here you will have certain components omega ij and some components omega 0I. Okay, because this object, of course, this ij, this has components omega 0I and omega ij. Because remember that this is anti-symmetric in ij, so there are 6 variables like this. This is 6. So aj anti-symmetric. Because it's an anti-symmetric 4x4 matrix, so 6 objects. And so this is, we can split these 6 objects between 3 objects and also 3 here, because this is also anti-symmetric. And so these are just in fact the boost and rotational components of the Lorentz algebra. So I have an object omega aj which is valued in the Lorentz algebra, so SO31. But you know that we can split the Lorentz algebra between the boost part and the rotation part. So this is just like, in these objects, some components are boosts and some components are rotations, in fact. And so by doing this combination of the rotation components and the boost components, with this gamma parameter which is here, and then using this redefinition, we obtain a very nice Hamiltonian formulation. So what we obtain is that the action, which is now a function of A and E, is just this. So T into X, and now we have E and I A dot A minus, I will explain what this alpha I minus L H minus M A H A. So remember that this A, these are A is a spatial index, and I is an SU2 index in fact now, because yeah, so these I indices are in fact SU2 indices. So the capital I are SO31 indices, but in SO31, by doing the split, we select a rotational subgroup of SO31, because this triad, this does not encode anything about the boost. This only knows something about the rotations. So SO3 or SU2. You know that SO3 or SU2 are the same thing. So SU2 is the double cover of SO3, so usually we call it SU2. And so this connection A, this is the Ashtekar-Barbero connection. And so what happens here is very powerful, in fact, because what happens is that we start with the formulation of gravity, so with a connection and a tetrad, but there, like, all the fields are valued in SO31. So SO31 is a non-compact group, because so a non-compact group means that when we parameterize the group, when we write group elements, one of the parameters will take values in a non-compact space. So here, because this is the Lorentz group, we have the boosts inside, and the boosts are parameterized by some parameter that lives in R, so a non-compact direction. But SU2 is compact, the difference with the Lorentz group. SU2 is completely compact. So it's very powerful because what we did is that we took Lorentzian gravity, so gravity with a gauge group which is non-compact, and write it as an SU2 gauge theory. And why is this a gauge theory? Because this is exactly the structure of a gauge theory. A gauge theory is something that is written in terms of the connection and the conjugate momentum. For example, Yang-Mills or electromagnetism or any such theory. So here the same thing happens. You have the connection A, which is an SU2 valued object, and the conjugate momentum E. So E encodes the metric, so E knows something about the spatial metric, and A is the gauge connection. And then on this space, we have constraints acting. So is it okay for the moment?
No, the alpha comes from alpha.
This is a multiplier. So these are, yeah. In fact, this is a. these are components of omega 0 in fact. So the time component of the connection. So I call it alpha. Yeah, alpha I is a function of omega 0. It's not important. But so now I want to tell you why this is really still gravity, why this is just a new Hamiltonian formulation of gravity. What is the reason for this? And what does it mean, in fact, to have this formulation?
Why it's so important to be compact?
It's important for the quantum theory because if you want to quantize a theory with a gauge group that is non-compact, with the techniques that we're going to introduce, or just the techniques of usual Yang-Mills theory, it's much more complicated when the gauge group is non-compact. And here it's completely, in fact, we don't know how to quantize the theory when the gauge group is non-compact. The only way to have it is to have a compact gauge group. And there are many reasons for choosing this formulation, in fact. So we can ask, okay, we have many ways of writing gravity. So this is one way to write gravity in the Hamiltonian formulation. But so from all the ways that we know how to write gravity, this is the only known way for which we can start to do quantum theory. All the other ways that we have to write gravity, there is no known way of quantizing them. And so one of the reasons is that the gauge group is compact now. The gauge group is SU2. That's one of the reasons. And the other reason is that the Poisson algebra of these variables is very simple now.
Just one question, brother. The physical constant, the classical physical constant, independent of the gamma parameter.
Yeah, independent. So what it means, in fact, yes, let me first tell you the physical content. So I will write these constraints. So Gi is in fact the covariant derivative. So this is A. So you recognize that this is just the Gauss law, in fact. This is a constraint, so this has to vanish. So it is a constraint because you know that when you have an action and when some variables have no conjugate momentum, there is no time derivative of alpha n and na. So it means that these alpha n and na are Lagrange multipliers. So if I look at the equation of motion with respect to alpha n and na, I get g equals 0, h equals 0, and ha equals 0. This is the reason for which these are constraints. And so if you look at what is the Gauss, what is this constraint, G is just the covariant derivative of E with respect to this new connection equal to 0. This is just the Gauss law. This is the SU2 Gauss constraint. This is why, in fact, sometimes we call this E the electric field. So usually people say that this formulation of gravity is in terms of a connection and an electric field, just like a gauge theory, just like a Yang-Mills theory, for example. And now H, yeah, maybe. It's not interesting to write H and HA, but let me tell you physically what this means. So what it means to have constraints is that you know that here, imagine that this is the phase space. The phase space of this theory. So on the phase space, we have a Poisson bracket, so a symplectic structure. And here the symplectic structure is just EIA. It's proportional to gamma. This is very important. Delta AB. Delta Ji. This is the Poisson bracket between E and A. But what is very important is that E and A, they commute in fact with themselves. So A. And this is the very powerful and nice thing about this formulation. Because if you don't introduce this parameter, in fact, and this additional term in the action, so if you use just the Hilbert-Palatini action for gravity, you do the Hamiltonian analysis, then you end up with a structure that is much more complicated than this. So in particular, you will see that the connection is not commutative anymore. So if the idea is to do canonical quantization, in fact, there is no way to quantize a symplectic manifold, so a Poisson structure that is completely not commutative.
You say that without gamma, this will not commute?
No, so these connections, they commute now.
Yeah.
But if we don't use this parameter gamma, so if you just use so this action, use just this action, then you get the phase space structure is not commutative. So the connection does not commute anymore. And so because there is this non commutativity, it is impossible to do a quantization of this theory.
But the gamma is not appearing there. I don't understand that. If you put gamma equals 0, then it does not commit anymore. Put gamma equal to 0.
In fact, here, so at this point we cannot anymore put gamma to infinity or gamma to 0 in fact. Now there is something non-trivial that happened when you are in this step, you cannot go back and remove gamma. In fact, the reason is that everything comes from the gauge fixing that we did in fact. The gauge fixing that we did enable us to get rid of the boost freedom in fact. Because in the Lorentz algebra, there are the boost and the rotation. When we put these components to 0, this is in some sense gauge fixing the boost degrees of freedom. So because of this is the reason for which all we end up with is the SU2 gauge rule. So just the rotational subgroup of the Lorentz group. And the boosts are completely eliminated. But if we use the Hilbert-Palatini action, if we do, for fun, if you take this action, do the Hamiltonian analysis, you will see that there are many second-class constraints. So if you're familiar with the analysis of constraints, you know that in an action there can be two types of constraints. Some constraints can be first class, and these are important for quantization because the first class constraints are the symmetries of the theory. So here these are all first class constraints, in fact. And these generate all the symmetries of the theory. So these first class constraints, they encode the dynamics of the theory. But there are also sometimes second class constraints. And in this action there are tons of second class constraints. And if you want to get rid of the second class constraints, because these are just redundancy, additional unwanted structure, the way to get rid of these second class constraints then makes the connection, this connection omega, not commutative. It doesn't commute with the Poisson bracket with itself anymore. And this is very problematic. In fact, what happens if you do this is that you end up, once again, after many steps, to the ADM formulation, essentially.
Even if you put the 0 I equals 0?
Yeah.
If you put the 0
Yeah.
0 is the same part.
Yeah. This is why, in some sense, even the Hilbert-Palatini action by itself is not enough to arrive to this nice Hamiltonian formulation. Because if you do this, once again, you end up with the ADM formulation. And it is not surprising because, as I told you, the reason for which this action exists is that E and omega are different variables. But in gravity, this is not natural because in gravity, the ADM formulation, there is only the metric. So when you do the Hamiltonian analysis, there are going to be constraints, and the constraints, they tell you that, oh, be careful, omega is not any omega, it's omega of E, in fact. So it's not any function omega, it's omega as a function of E. And once we write omega as a function of E, we end up again with ADM variables. And the ADM phase space, there is no known way of quantizing this.
But to begin with A independent of omega, and then you obtain that omega is a function of A because of the second class constraints.
Exactly.
The second class.
Yeah. So here in these dots here, this long step, you have to solve the second class constraints.
And then you obtain that omega is a function of E.
Exactly. And then this omega as a function of E is highly non-commutative. It doesn't commute at all. So here it's commutative. And so you can ask the question, but where are these constraints here? Because there are also, in fact, once we go from the host action to this formulation, there are also certain second-class constraints. And these second-class constraints, they can be solved explicitly. And what they tell you is that, in fact, there is a way of writing this now. This, in fact, you can show that this component, sorry, just omega. So in fact, what are these two objects? This, in fact, is the spatial Levi-Civita connection. So it's written in the internal space again. And this is the extrinsic curvature. So these are ADM variables, if you want. If you do the ADM analysis of gravity, we have as a natural object, we have the Levi-Civita connection, and we have the extrinsic curvature. And so I choose this way to present the thing, but in fact, historically, the way this was introduced was by doing a canonical transformation from the phase space of ADM gravity to this phase space, in fact. This is how historically it was introduced. So people historically just took the ADM phase space. So in the ADM phase space, the variables canonically conjugated are in fact the curvature K and E. And people said, okay, now let us do this canonical transformation, and you can show that the resulting structure is given by this. What is very interesting about this canonical transformation is that the connection is commutative. And this is a very non-trivial fact, because you see that the connection depends on E, in fact. So it depends on this capital E. So it's not trivial that the connection commutes with itself, because imagine that I commute two connections, so I compute this Poisson bracket. So this A knows about E, in fact. But in such a way, there is a clever combination that makes that in the end, the result is 0. But a priori, if you look at this, yeah, A knows about little e. So little e is like capital E if you want. So this in fact is that EIA. So the connection A knows about E, but not entirely. There is this part which is independent, which is the extrinsic curvature. And so now to go back to this phase space, you know that in gravity, or in any constraint theory, once you have a phase space, so you have a point here in the phase space. This point here is AI. This is a configuration for the gravitational field. You give me one EA, I, and A. You give me the electric field and the connection. You have specified the configuration of the gravitational field. But we know that these variables are not completely free. They are subject to these first-class constraints. So in fact, in the phase space, there is a subspace here. There is a subspace. There is a surface here. And this surface is constrained equals 0. This is the hypersurface of the constraints. So on this surface, the constraint G is equal to 0, H equal to 0, HA equal to 0. But now you also know that since these are first-class constraints, so because they are first class, they generate gauge symmetries. So this means that if I look, for example, at the Poisson bracket between G and E, this will be an SU2 gauge transformation. This is a gauge symmetry. The Poisson bracket between G and A is also an SU2 gauge transformation. So because of this, if I choose a point here, there is an orbit, in fact. There is this trajectory in phase space that is completely physically equivalent to all the other ones. So all the points here are physically equivalent because they are related to gauge by gauge transformation. So you know that, for example, in Yang-Mills theory or in Maxwell theory, the Gauss constraint is the generator of gauge symmetries. Because if you look at the Poisson bracket between the Gauss constraint and the electric field, or the connection, you will get an SU2 or a U1 gauge transformation. So here we could show that the same thing happens. And so now what we can do is count the degrees of freedom, see why this is really a formulation of gravity. And the reason for this, so first you could ask me, why we have this additional constraint? Because in the ADM formulation, we don't have this constraint. In the ADM formulation, we just have the lapse and the shift. So we just have, this is evolution in time, and this is evolution on the spatial slice. So why now do we have this extra constraint? Well, it's natural, because this extra constraint is just the freedom now of doing rotation in internal space. So it's just a normal constraint that appears because we are putting additional indices. We are working with connection and conjugate momentum, and so these, they live in this internal SU2 space. So because of this, there is a freedom to do SU2 gauge transformations. And the SU2 gauge transformations are encoded or generated by this Gauss constraint. This is why it has only internal I indices, this constraint, because it only acts on the internal SU2 indices. So what we can do is count now the degrees of freedom, count what happens. So you know, for example, for our usual gravity, so ADM, so the variables are P, AB, and GAB. So the spatial metric and the conjugate momentum. And so this is in fact, so this is 12 variables, because this is AB, A and B go from 1 to 3, and it's symmetric. So this is, so 6 components and 6 components. This is 12 variables. But we have constraints. The constraints are scalar constraints and the vector constraint. So again, this one generates time evolution, and this one generates spatial diffeomorphisms. But there is one constraint like this one, and there are 3 constraints like this one. This is one constraint, and 3 constraints. So what we have, in fact, is that the physical degrees of freedom, so the physical degrees of freedom is given by, so any generic point in phase space, so 12 minus, so 3 plus 1, but it has to be times 2 in fact. And why times 2? Because these are first class constraints. And when we count the degrees of freedom, the first class constraints have to be counted twice. Why twice? Because they do 2 things. First of all, they define a constraint hypersurface. This is just saying that this is an algebraic relation between A and E. So we can use one relation to write some E in terms of A. And here we can use 3 relations, so 3 equations, to write some E's in terms of A's, if you want. So this is just like an algebraic relation. But then once we do this, there is still this freedom. Once we are on this constraint surface, these constraints, they generate by Poisson bracket this flow going through all the gauge equivalent configurations. So because of this, we have to count once again these constraints. This is why there is this times 2 in fact. So first class constraints, we count them twice. And so that the result, there is no mistake, is 4. And 4 is the right result, because 4 is just, so in the phase space, we have two polarizations of the graviton and the 2 conjugate momentum. So this is why we have 4 here. And here we can do the same counting, in fact, to see that it's always nice to do the counting, because then we see if we have a mistake or not. If we find 36, for example, it's completely wrong, because this means that this has 36 degrees of freedom. But gravity has only 4 degrees of freedom. So now we can count, and so the A, IA, this is a 3I indices and 3A indices. This is 3 times 3. And EAI is the same to this 3 times 3. So this together is 18. So 18 variables are probably 18 independent variables, but we have these 3 constraints. So the Gauss constraint, this is 3 constraints, because I goes from 1 to 3. This is only 1 constraint, and this is 3 constraints. So 3 plus 1 plus 3, this is 7. And now we can see that the degrees of freedom is 18 minus 7 times 2, so it's 4 again. So this 4 is really the same 4 as this one. This tells us that with this Hamiltonian system, I described the same thing. I described gravity, but written in a very, very different way. Huh?
Just because, okay, you said that you have now a compact group, but anyway, you still have diffeomorphism invariance, and that's the main problem with EM or any quantum derivative.
Yes, a priori there is still, so it did not simplify that much. It's not, so now it's not trivial to quantize this, but at least we have a well-defined starting point. It's very important when we do quantization to have a nice starting point, because again, the entire spirit of quantization is just to do this. In fact, you take, for example, P and Q, you transform this into a commutator, and then you take all the constraints. C, you transform them into quantum constraints. And then you choose some polarization. So you say, okay, my wave function depends only on Q or P, for example on Q. Then you apply the constraints. You look for this. This is, roughly speaking, the procedure of quantization. So it's very important if we do this to. Yes, in fact, what happens when you do this, if you think about usual quantum mechanics, for example, one free particle, so Q and P are the variables. When we do this, we always use the Schrödinger representation. We always say that the Q acts by multiplication and the P acts by derivative with respect to Q. But there is a very non-trivial statement here, because to do this, we have to first find a Hilbert space on which these operators are acting. And then we can look for this action and say how exactly they're acting and is it unique or not. We can use different representations. But there is a theorem, in fact, that tells us that for finite dimensional systems, the representation is unique, in fact. There is only one, up to unitary equivalences, there is only one unique representation, which is the Schrödinger representation. This is why in usual quantum mechanics, we never think about, we always take the L2 Hilbert space and then Q act by multiplication and P by derivative. We never try to do something else, because all these representations are equivalent. If you do something else, you will always get the same physics. But for infinite dimensional systems, this is not true anymore. This theorem doesn't work anymore, and so we have to be much more careful when we do these steps. We have to really find like good classical variables, promote them to commutators, and then really be careful about the way they act on the Hilbert space and how to define this Hilbert space. So we're going to see that with these variables, it's much more convenient, and it's the only known way to do this construction. And so now once we have this, we have the program in mind. But we see what is going to happen next. What has to happen next is to do this Dirac quantization. Try to apply the quantization program. So we have to do now, so this EA, transform this into a commutator. And also we have to transform the constraints into operators. And then we can do this. We can find what we will call the kinematical Hilbert space. Then we impose the quantum Gauss constraints. Then we find what we call the gauge invariant Hilbert space. Then we impose diffeomorphism. Then we find the diffeomorphism invariant Hilbert space. And then we impose the remaining constraint, and then we end up with the physical Hilbert space. So this is the program now. This is what we try to do now. So yes, what I wanted to derive is really this Hamiltonian formulation, because this, what we showed is that this is equivalent to usual gravity. It's just another formulation of gravity, but classically it is a completely acceptable and valid formulation of gravity. It has the advantage that it has only first-class constraints, so very simple structure of the constraints. It has a compact gauge group, so these objects they live in SU2 now. This is very important. And the connection is commutative. So Poisson bracket between A and itself is equal to 0. This is very important. Yes, so it's 4, so maybe. Yeah, so if we talk about loop quantum cosmology on Friday, today I just want to derive. It's 3 or 4, it's 4.
We still have almost 1 hour.
Oh, yeah, it's 3, okay, that's 4.
40.
Yeah, so do you have any questions about the classical? Yeah?
So in the end, it seems that the absence of second-class constraints is directly linked to the complexity of the group.
No, because in fact, it's a good question, but in fact there are still second-class constraints, but we can solve them. And when we solve them, we say that this is equivalent to this, in fact. So in fact, we didn't do the analysis properly because it takes a very long, not so long, but it's not very useful, but what we see is that one of the second-class constraints that we obtain is that the covariant derivative of the triad with respect to these components is equal to 0. And this is the this means that the connection, this connection is E compatible. So it's the Levi-Civita connection compatible with E. So in fact, there are still second-class constraints, but we can solve them explicitly, and the resolution just amounts to saying that these components is the Levi-Civita connection. This is why in the end we end up with first-class constraints and everything is nice. But so historically, this was found the other way around. Historically, first, people took the ADM phase space and said, okay, this phase space is not suited for quantization because on this ADM phase space, the variables are the spatial metric and the conjugate momentum. And I don't know what it means to have a wave function of the spatial metric. I don't know how to write the constraints in terms of these operators, so it's hard to do quantum theory. So people said, okay, can we find another point of view, another formulation which looks like a gauge theory? And they found out that by doing a canonical transformation, so on the phase space of ADM gravity, we can end up with this formulation here. And so essentially, this canonical transformation was equivalent to this, in fact. So taking this combination of the Levi-Civita connection and the extrinsic curvature. And then only a few years later, I think even 10 years later, Holst, so who found out this action, he discovered that, oh, we can derive this Hamiltonian from a Lagrangian, so from an action, which is this Holst action. So we just have to take the usual Hilbert-Palatini action, add this 1 over gamma term, and then this topological part. Then he said, okay, if we take this Lagrangian, then we choose this gauge fixing, we choose this gauge which fixes the boost, and then we end up with this formulation. So some people present this starting from the ADM phase space, but sometimes people do it from the Lagrangian.
Perhaps the main point of that is that the age there is much more simple in this. It's much simpler in these variables than in the old ADM.
Yeah, exactly. So now, this was in fact the original observation by Ashtekar. Ashtekar, when he wrote down these variables, he did this because it looks like a gauge theory, so we can use techniques of gauge theory to quantize this, and also because the Hamiltonian is much simpler. In fact, it's polynomial in the variables, almost polynomial. And this is why it's much simpler. The ADM Hamiltonian is completely hard. It has like inverse of square roots of the metric, and so there are many ordering ambiguities and regularizations involved. And this is why we don't know how to make sense of this, the quantum operator corresponding to this. But here this is almost polynomial, in fact. And so, yeah, I can say just one remark about this gamma, in fact. What happens is that, now you can ask, something strange happened. You can tell me, wait a minute, it's very strange, because now this is SU2, so a priori this doesn't know anything about the space-time signature. Because at first I can start with the Lagrangian that is Lorentzian or Euclidean, so SO4 or SO31, but here it's SU2, so I lost the information about the signature, in fact. But in fact, no, because all information is contained in the scalar constraint. If you look at the constraint, in fact, if you look at the constraints, they're here. Okay, so this constraint. This constraint is and the Hamiltonian constraint is epsilon. And so this plus minus, in fact, is only, this is the only place where you see the signature. So So if you start with a Lorentzian signature, you will have a minus here. And if you start with a Euclidean signature, you will have a plus here. So it could seem strange because everything is SU2. So we lost. So okay, well, how do I know like the gauge group with which I started? And I know because in the Hamiltonian constraints, there is a sign that propagates everywhere, and the sign ends up here again. So the only place where we can see the difference is only in the sign. And you also see something very interesting here, and very interesting is that there is this term here. So you see that if I take gamma equals to I, so if we take, this is 0, gamma equals plus minus I. And so if gamma equals plus or minus I, this is 0, and then this is completely polynomial in the variables. It's just E. But the problem is that there is a deep reason for which we can take gamma equal to I, plus or minus I. And this gamma equals plus or minus I corresponds historically to the very first Ashtekar variables. So at first when Ashtekar did this, he worked with a complex connection. He didn't choose gamma real, he chose a gamma complex in fact. And where does this come from? This comes from the fact that, in fact, the Lorentz group, so SO31, can be decomposed into two, what you call self-dual and anti-self-dual copies. And these are they form two SU2 subgroups. So we can write this as SU2 complex plus so in other words, like every Lie algebra object like this, omega Aj, can be written as a, you can replace it by omega plus I and omega minus I. And the plus and minus are what we call the self-dual and anti-self-dual components of the Lie algebra. And the definition, in fact, of omega, yeah, this is interesting. So the definition of omega, so plus minus I, is something like this. It's 1/2. Okay. Plus minus I. This is just in the Lie algebra, the decomposition. So I can take a Lie algebra valued element, omega Aj, and I take the boost component and the rotation component. I do this complex combination, and I get the self-dual and anti-self-dual components. So these form two SU2 Lie algebras that commute with each other. They don't. So the plus and minus part, they don't see each other. They completely commute. And you see that if you look at this expression, this is exactly, in fact, the Ashtekar-Barbero. So the real connection with gamma equal to I, in fact. So in this formulation, if I take gamma equals to I end up again with this formulation. So the Ashtekar formulation, the original one, in terms of the complex connection, and without this problematic part. But the reason for which it's hard to do this is that if you do this thing, then the gauge group becomes non-compact again. Because this SU2 complex, it's SL2C, it's SO31, it's the Lorentz group again. So it's not compact, and then we cannot do quantization anymore. And also when we do this, the variables become complex. So because they are complex, we have to add what we call reality conditions. So certain constraints that tell us that, in fact, the metric is not complex, but really real. And so these conditions, we don't know how to handle them. We don't know how to work with them, and they're very complicated. This is the reason for which, in fact, this complex formulation was abandoned. And then people said, okay, is there a way to have this formulation, but with a real, not with a complex variable, but with the real variables, and with a compact gauge group? And the answer is yes. The answer is yes. I can simply replace this I here by a gamma, and then this becomes the phase space. So the only problem when I do this is that I get this additional part in the Hamiltonian. So if I work with gamma equals to plus or minus I, this part simplifies completely, and the structure is simple, but then I have a complex variable and a non-compact gauge group. So the way to overcome this problem is to take a real parameter gamma, not complex, not plus or minus I, but any real parameter, and then the price to pay for working with this real SU2 connection is to have this additional, bit more complicated structure. In fact, it's not that problematic. We know how to regularize and how to quantize this operator, and this is well understood. And so this is the link, if you want, the reason for which here we have SU2 as a gauge group. It's SU2 because if I take again gamma to be complex, I get the complex SU2 which corresponds to this decomposition here. And the way to make it real is to use this formulation.
So in that formulation, gamma is real.
Yeah, gamma is real. So here gamma. So is this real gamma? Okay. And so now we can go to the quantum theory and we can start this program of quantization and see what happens. Okay, so one other remark about the symmetries, when we say that these constraints that generate the symmetries of the theory, this means that, for example, if I look at the Poisson bracket between this constraint and what I can do is define H n, which is defined by the integral of the sigma n a of x, h of x. If I introduce this object, I can compute the Poisson bracket between H and the connection. And so this is just the derivative in the direction n of the connection. This is what we mean by when we say that this constraint is this constraint HA is the generator of spatial diffeomorphism. This is what it means. It means that if you look at the Poisson action of this constraint on the phase space variable, I get a diffeomorphism. I get the derivative along this direction. So this is just what it means. Okay, so now we can start the quantum theory. Now to go to the quantum theory, what we have to do is to do something with this Poisson bracket, in fact. This was the Poisson bracket between the variables. This is where the idea of the loops, or the name loop quantum gravity, comes into the game. So what happens is that it's not proper to use these variables as they are. They're not suited for the quantization, not yet. What we have to do is define a smearing of these variables. So take these variables, but take a slightly different definition, which makes them more regular, in fact, more suited for the quantization. And the way to do this is that you can notice that so A is just a connection. So A is a one form. So A has one spatial index. So it's a connection. So a connection is in fact always a one form. A connection is a one form which takes value in certain Lie algebra. And this is an SU2 connection. And so because it's a one form, there's a natural smearing of this connection, of the one form. It's just to integrate it along links, along a path. What we can do is replace the connection A by what we call the holonomy. Which is just the exponential, so H, we write it like this, along the link L. It's just the exponential of the integral along the link of the connection A. And the reason to do this is essentially that, see that if I take the exponential of a Lie algebra element, so this A, this connection A is a Lie, so A written like this, is in fact A I A, so on the basis of one forms, and then tau I. And tau I is a generator of the SU2 Lie algebra. So if I take an element of the Lie algebra, so SU2, and exponentiate it, I get an element of the group. So this is a group element, this is a holonomy. This is an element of SU2. This is an element of SU2. similarly, we can look at this electric field and see that this E is a combination of two triads. So because of this, it's a two form. There is one form here, multiplied by another one form. So this E is a two form, in fact. And so this E, because it's a two form, it's naturally integrated along the surfaces now. So a two-dimensional object, so a surface. So we replace E by what we call the fluxes. So the flux is the flux of the electric field across a certain surface. So you give me a surface, you choose a surface, then we can define so this flux, so x xi, so a certain surface S, and normal to the surface, and S sigma is just the coordinates on the surface.
But without the exponential.
Without the exponential, yeah. Without the exponential. The reason for doing this is that in fact you want to look for a representation of these objects, so of the Poisson algebra, on a certain Hilbert space. And usually, so already in ordinary quantum mechanics, you don't have to start with P and Q as your operators. You can choose exponential of alpha P and exponential of beta Q. Instead of having the usual Heisenberg algebra, you can choose the Weil algebra. The Weil algebra is by exponentiating the generators. And then once you do this, you can look for the representations of these new operators, which are just the exponentiated version of the usual operators, usual variables. And so depending on what you do, you will find it easier or harder, or maybe impossible, to find a representation of the quantum algebra. And so here it turns out that the only way, so if you use this variable, if you use this exponential of the connection and this flux here, we can find there is in fact a result of uniqueness. There is a uniqueness of the kinematical structure. So there is a unique representation of this, what we call the holonomy flux algebra. Then this will become a quantum algebra of operators. There is a unique representation of this quantum algebra on a certain Hilbert space, which is constructed from SU to infinity. This is a very powerful result in quantum gravity, which is that the kinematical structure is unique. Once we use this, these as our basic variables, our basic operators, then there is a unique way to do quantum theory in some sense. There is a unique representation of this on a Hilbert space. But for this, we have to use these new, these slight modified variables. And we will see the reason why we want to use holonomies of the connection, because these are SU2 elements. And then this will make things very powerful. So now what we can do is to look for, first we have to choose a polarization. We have to say if our wave functions are going to depend on the flux or on the holonomies of the connection. So what we said is that the wave functions are going to be, we look for functions or functionals of the connection. So you see that the holonomy is already, this is already a functional of the connection. But what we're going to do is to use the quantum configuration space is going to be what we call the space of cylindrical functions of the connection. So what is the space of cylindrical functions? It's the space of functions which only depend on the connection through their holonomies along certain links. So how to construct this? To construct this, I need to choose two things. So choose a function f, and choose a graph gamma. So this gamma is a graph now, it's not the connection. And once you choose a function and a graph gamma, you can define a state now, psi, gamma and f, which is really a functional of the connection. which depends on the holonomies of the connection along all the links. So we write this down explicitly, like H2, H. For example, I choose a graph like this, so with links. So the links are oriented, they have a beginning and an end point. Put an orientation here. This is the graph gamma, and there is a link L1, a link L2, a link L3, link L4. Now for all of these graphs, I can construct the holonomies of the connection. So whenever I have a link like this, I can take the connection A, and I compute the holonomy along the link L1. Just by doing this. Then I take the link L2, and I compute the holonomy along the link L2. Then I take all these holonomies and I put them in this as arguments of this function. This is how this state is constructed. These are basic quantum states.
What means this graph? What is this graph?
We'll see later on what it means, but it's a way to capture certain information about the phase space variable, about the connection. So because I asked you like what is a state for you? So in quantum theory, what is a state? So a state is a function of, for example, say the position. So you have to specify what the state is. So here to specify the state, the same thing happens, but to specify the states, you have to specify the links along which you are going to compute these holonomies. You have to tell me what the links are. If you tell me what the links are, then I can compute this state. And it is, if you want, an assumption. So this is, some people call it the loop assumption. It's the assumption that the degrees of freedom, the variables to use for the quantum theory, are given by all these holonomies along these links. So the first thing that people did historically was to take this function to be just a trace. So the trace of one closed loop. So look at this. There's only like one link. And the functional f to be the trace. This is why the approach is called loop quantum gravity. Because first people use these Wilson loops. So these are the analog of the Wilson loops in Yang-Mills theory to construct by holonomies of the connection. But so there is, in fact, people notice that there is a more general way of doing this. Instead of working only with these closed loops, you can just give me like a graph like this. It's more general. It's much more a natural way to write down the quantum states. So we will see later on what this means, in fact. What is the meaning of this graph? And we see that this graph, in fact, encodes the quantum geometry.
But the number of the graphs are completely arbitrary.
It's arbitrary, yeah. So if I ask you to write down for me a kinematical state, so a state of gravity at one instant of time, you just have to give me this graph, this information. This graph is the holonomies of the connection. You don't have to know the connection at all the points. You just have to give me a graph. So if you want, now we're introducing a discrete structure. So I'm introducing a discrete structure by hand. I'm choosing a graph, and with this graph and this function, I construct this object, this function. Then we will see how this is related to the continuum, to the case where we sum over all the graphs. Later on, we are going to take a sum over all the graphs, and in some sense eliminate this extra structure, these graphs. But for the moment, I have to specify this graph to you. And we will see why these graphs are useful, why it's very convenient to write the states in this way.
So a state is a specification of the graph and of the function.
Yeah. Exactly. So now once we have these states, so this in fact is an element of this gamma, what we call SIL gamma. SIL gamma is this mathematical object, is the space of cylindrical functions of the connection. And what does it mean to be a cylindrical function of the connection? It means that it's a state that depends on the connection only through its holonomies along certain links. So it's not a state that depends on the connection at all the points of the spatial space, but only certain discrete information about the connection. So you only know the connection along these links. So you have connections that live everywhere at all these points, but you don't want this. This is like too much structure if you want. It's enough to just work with the knowledge of this, the connection along these links, along this link, along this link, along this link. If you specify this, you specify an element of this space of cylindrical functions. And now the role of the game is to turn this space of symmetrical functions into a Hilbert space. And the way to turn this into a Hilbert space is to find an inner product. We have to find a product to multiply this, write down the inner product between two such states. And this can be easily done because now we're dealing with SU2 elements. So you can see that this f, in fact, what is this f? It's a function of, so f goes from SU2 to the power L, just a number. So because f has like L, n, so n links, so n arguments. So this lives in SU2, this lives in the group SU2, this lives in SU2. So this f is a function from SU2 to the n, it just gives you a number. But on SU2, in fact, we know how to do harmonic analysis on SU2. And this is known because there is a theorem which is very powerful for compact groups. This is why we wanted to work with compact groups. That tells you that what we're looking for in some sense is now a basis, a convenient choice of basis in this space of symmetrical functions. And it turns out that the way to get this basis is to use the Peter-Val theorem. And so this this theorem tells you that you can write the function on SU2 or on any compact group. In fact, here it's SU2 as a combination of some coefficients on a basis, and this basis is given by the unitary irreducible representations of SU2. So you have this SU2 compact group. It has unitary irreducible representations, so indexed by the spins J, so half-integer spins. And these representation matrices, they form a basis of a Hilbert space. So this means that any function, so f, so let me write this. Yeah, so just before doing this theorem, you can first think of like how to. So if you want to turn this into a Hilbert space, so the space of symmetrical functions into a Hilbert space, we have to specify an inner product. And there is a natural inner product on SU2, which is given by the Haar measure on SU2. So we can integrate functions over SU2 with a natural measure on compact group, and this measure is the Haar measure. So if you choose a certain, so an SU2 group element takes a different form depending on which parameterization you use for writing down the group elements. You can use, for example, the Euler angles on the 3 sphere, and then the group element of SU2 has a certain expression. And then there is a metric, in fact, on the group SU2, which enables you to integrate functions in SU2. This is a well-defined process. And so what we can do, in fact, is to define this inner product, gamma f1 in state gamma f2,